As we finish up Chapter 11, one of the most important concepts we can start to work with is curvature, represented by the letter kappa. So that we look at this simple parabola, and that you can see as we work across and let t grow, that the value of the curvature increases as we hit that curve. Right? So the curvature is measuring how quickly the trajectory changes, in other words, how much bend it has. So that as we look through the concepts and get more complicated figures, we would say that if we show the tangent vector of this particular trajectory, is that we can see if we have a unit normal vector pointing in the direction of travel, that the normal vector will point into the inside in the direction in which the curve is changing. So not only does it go inside, so let me see if I can get the z component here, that you can see that it's also changing in the components so that I can move inwards as well as all directions, so that that normal component is always pointing in the direction that the curve is turning. Okay, so that as we get more sophisticated with our figures, you can see this is a helix, so we can tell that by having our circular components in the x component cosine, circular component in the y component, and then just letting the vertical component grow with this variable b. So that the dot product is 0 of the unit tangent and the unit normal, which means that they're orthogonal, and that the tangent points in the direction and the normal points towards the inside of the curve. So as we grow this helix, or let it kind of grow up, is that normal vector is always pointing inwards, so you can tell which way the direction is changing, and that the tangent vector is pointing along the curve. Right? In this figure, we actually break that acceleration component into its own components, the tangent component and the normal component, with a simple parabolic trajectory, letting the x component be t and the y component being t squared. So as I go around this bend, that acceleration component is always moving upwards, but that if I now break this into its tangent and normal components, that it will show which way this curve is changing. Okay, so here's the normal component, always pointing towards the inside of the curve. Okay, so that these tangent and normal vectors create a two-dimensional orthogonal system, and all we really have to do now is add our third dimension. And we do that by adding this b, the binormal vector. So this is a kind of just a W shape, or whatever you want to call that, and that and let me put in the tangent and the normal, so we know that those point along the curve and towards the inside of the curve, and that they create a orthogonal system of just the two of them. Okay, so now let's add, let me just move this around this way, and then look at the binormal component. So what this does is add a third orthogonal component, that is a vector b, that is orthogonal to both the unit tangent and the unit normal vectors. So now we have completely specified the three-dimensional orthogonal system with these three vectors, the b and t frame. So that each of these, let me turn off the normal and the binormal, and the tangent itself defines a plane called the osculating plane. So that along here, so that not only do we get an orthogonal system of vectors, but now we also can create a planar system of each of these three planes, and allow us to have kind of a referential frame of reference, so that we can move along the trajectory and keep our three-dimensional orthogonal system of components. A circle is a special case of this, in which when I create all these things, the curvature stays constant as I go along around the curve. You can see the curvature, and the torsion, in other words, the amount of which the curve leaves the plane, the osculating plane, which is described by the torsion tau, is 0 because I'm staying in the plane, right? For a helix, that would be different, because I would be torsioning out of the plane and I would have a non-zero tau. So that if I look at now this dt ds, now if I use the letter s, that means that I have using arc length as a parameter, and I just get this little, let me put it back into motion here, the t vector here, which is pointing away as the t, let me put the other two on, the b component, and each of these is a component in arc length that tells us what is going on in each of them, right? So now remember that when you use the s, that means that I'm using arc length as a parameter. In other words, the speed is 1. Okay, so as I go across here, let me leave the panels on now, or the planes, so that you can see how that changes as that circle goes around. Okay, so finally, I just want to look at this figure, which is the same idea, but now I have a helix. So you can see that I'm leaving the plane here, so my torsion is non-zero, and that the curvature is just a little bit less than the circle. So let me put that on, put that in motion, and then put the planes on there. So you can see how that osculating plane is going along with the tangents, showing me how my curve is increasing. The normal component is creating the normal plane, showing how the curve is changing, and then the rectifying plane is showing how the binormal vector changes. Okay, so let me turn off the planes, and then we'll put on our individual elements here and do the same thing, so that they just show that same kind of process, but now with using the arc length as a parameter. In other words, the speed is 1 when I talk about ds. Okay, so that's just a little bit of a geometric or graphical representation of these complicated ideas that we're working with as far as the TNB frame is concerned. Okay, so